The following questions will be done throughout this video. You just need to look at the timestamps and see which one you're going to be going through. If you want to do question 1, it'll be in worked example 1. Question 2 will be in worked example 2. Pretty straightforward. Let's get straight to the introduction. Okay, so when we see these integrals, and let me open this up over here. When we see these integrals, let's look at the following, right? Let's look at the difference here, okay? So what do we have here? The numerator is actually just 1, right? 1 dx for both of them. Normally we would just take the dx outside, right? But in this case, let's just leave it there for now. Let's look at the standard forms. Let's look at this integral right here, okay? This one with the denominator, the only difference over here for this denominator is that this one has no squares. This one has squares, okay? So what are we going to be doing from here? Well, I'm not going to explain it in full detail, but I'm going to show you the process of how we're going to be doing it, because there's a lot of visual proofs that you can find on the internet, but unfortunately I don't have the software to do the visual proofs. So I do recommend checking out the visual proofs. It's really nice. So what are we going to be doing from here? So if we see the denominator in some form like this, we will suppose that t is going to be equal to tangent of x over 2. So it's the double angle of tangent, right? But what if we had the squares instead? If we had squares, we would suppose that t would be equal to tangent of x, just x this time, okay? And if we want to consider domains, if you want to, we're saying that x, in our case over here for the double angle, will lie between negative pi over 2 and positive pi over 2. Whereas this domain here for x is where x will be lying between negative pi and positive pi. Okay, that's just out of your, if you are curious about the domains of the functions. So I can't really explain everything right now, like as the introduction, but I think it's better that we go through the worked examples and then we do it step by step, and then you'll see the pattern. You're going to see that we're kind of applying the same thing for both these questions. So let's get straight to the first question. Okay, now with the ones without the squares, it's a little bit more trickier than the one with the squares, and that's why I wanted to do this one first, so that we can deal with that. And then afterwards, when we're used to all of this, we kind of want to refine our knowledge a little bit by doing another one with the squares, and you'll see that it's going to be much more simpler to integrate from there. But let's just get started. How are we going to start now? Now, whenever we're working with the substitution, the t substitution in our case over here, first of all, we are going to suppose that t is equal to tangent of x over 2, because we don't have any squares, right? There's no squares. But what are we going to do from here? Because now we have tangent of x over 2. Where does this come from? There is no tangent here. Like, what are we going to do? How are we going to manipulate it? Now, this is what we need to consider. We are actually making reference to some right angle triangle. And like I said, the visual proofs there, they do have it on YouTube. You can check it out. We're considering some right angle triangle where we have one angle, which is x over 2, okay, with sides of 1, t, and then what is this side going to be? So we know this side, which is t, and this side, which is 1, so we just need to find this using Pythagoras, right? We need to find the hypotenuse using Pythagoras, and I'm not going to do it right now because I'm pretty sure we all know how to do Pythagoras by now. So we are actually going to get the positive square root of 1 plus t squared. Okay? Pretty straightforward from here. What do we do next? So clearly, what we are actually doing at this point here is we are actually going to use this right triangle, right? So we use the angle, the half angle here, but we are going to use the right triangle to actually substitute in for what we have in the denominator. But just follow my steps here and then you'll kind of understand it. Then you're going to be following these steps for every single question that you answer based on the substitution. So like use substitution, we kind of want to replace the dx because we want to put t into the integral to make it simpler and easier to integrate. So we need to replace dx. And in order for us to find dx in the first place using this equation is to differentiate on both sides. So if we use implicit differentiation, we'll have dt is equal to secant square of x over 2 multiplied by, so you're using chain rule, the derivative of the inside. The derivative of, so let me write here, the derivative of x over 2 is the same as saying the derivative of a half x, like so. And now we know that the derivative of a half x is just equal to a half. Okay, so this means we are multiplying by a half. Okay, where we'll just write the half here. Okay, cool stuff. So here, and also we have this with respect to x. So there's our dx. Now we just need to solve for dx, in our case over here. So let's just take this 1 over 2 over to the other side. We multiply both sides by 2, so that we'll be left with dt is equal to, and now the half will cancel, and then we'll have secant square of x over 2 dx. Now what are we going to do from here? Because remember that we had tangent of x over 2. But what are we going to do with the secant square of x over 2? We need to recall our identity that tells us that 1 plus tangent square of x is equal to secant square of x. Okay. So we are saying that secant square of x over 2 is actually just going to be 1 plus tangent square of x over 2. That's what it's going to be. Obviously, what we are doing is we're just going to be halving the angles on both sides. Okay. So now we are actually going to do the replacement here. We are going to say that secant square of x over 2 is the same as saying 1 plus tangent square of x over 2 dx. Okay. So it's going to be 2 dt. And remember that tangent square x over 2 can also be written as tangent of x over 2 all squared. Okay, and we know that tangent of x over 2 is equal to t. So we can just replace tangent of x over 2 with t. So then we're going to get 1 plus t squared dx, which is equal to 2 dt. Okay. And then from here, like I said, we're trying to find dx. So we're going to take the 1 plus t squared to the other side. So we're going to divide both sides by 1 plus t squared, so that we are left with dx being equal to 2 dt divided by 1 plus t squared. Okay. Perfect. We found dx. And guess what? This entire side here is in terms of t, with respect to t. That's perfect. That's exactly what we want at the moment. So now what are we going to do? We can actually just plug it in over here to our integral. So that's what I'm going to do, right? We are going to have the integral, so it's going to be now the integral of 1 divided by, we're going to have, it was 4 cosine of x, right? So it's 4 cosine of x minus 3 of sine, 3 times sine of x. So 3 sine of x, like so. And then remember, we add dx, which is equal to 2 dt over 1 plus t squared. Let's write that a little bit neat. 1 plus t squared. Now we have one issue here. The issue that we have is that we have cosine of x and sine of x, which is in terms of x. And that's our biggest problem. But the question is, even if we wanted to do a substitution for that, we only have substitutions for when we have an angle of x over 2 and not just x. So how are we going to actually manipulate it so that we can get cosine of x and sine of x? So paying very close attention to what I'm going to be doing, okay? Here, I'm going to look at how are we going to get sine of x, or let's do cosine of x. How are we going to do cosine of x? Using what we have over here of cosine of x over 2. So what are we going to do with this expression in the angle to get just x? Well, in order for us to get rid of this 2, we need to multiply this whole thing by 2. So we can actually rewrite it as 2 multiplied by x over 2. Okay. So we are actually saying that cosine of x is equal to the double angle of cosine of x of x over 2. Okay, so we take this 2 outside of the bracket and then we get this. We can do that. And then we can just express this double angle cosine as the following. We need to remember that our double angle of cosine, we're going to use one of them, which is this one, it's easier, is going to be cosine square of the angle, which is x over 2, minus sine square of the angle, which is x over 2. Okay, remember we're still having with respect to the angle x over 2. So we are saying that cosine x is equal to this. Okay. Cool. And that's perfect. So let's kind of rewrite this. Actually, no, we don't have to rewrite it. So we actually now have cosine of x over 2 all squared, and we have sine of x over 2 all squared. And we can actually find cosine of x over 2 using the right angle triangle and sine of x over 2. So let's do the substitutions, shall we? How do we find cosine of x? We're just going to plug the stuff in from the right angle. So here, for cosine, we're going to use the adjacent over the hypotenuse, which is 1 over root t squared, 1 plus t squared. But remember, we're squaring it. So it's going to be 1 divided by root 1 plus t squared, all squared, minus the sine version is going to be where we use the opposite. So the opposite over the hypotenuse, which is t over root 1 plus t squared. So t over root 1 plus t squared. Whoa. All squared. Okay, remember that's the square that we have. Cosine of x is now going to be equal to, we're going to take the square in to both the numerator and the denominator using the properties of exponents, such that we're left with 1 square, which is 1, divided by, squaring a square root means we're eliminating the square root. So it's going to be 1 plus t squared, minus, it's going to be t squared divided by 1 plus t squared. Okay, same thing with the other denominator. Okay. And then from here, let's write this as one fraction. So it's simple, right? So we can rewrite it as 1 minus t squared divided by 1 plus t squared, which is equal to cosine x. Okay. Okay, that's as far as we can go right now. Okay. So now we have cosine of x, right? We have cosine of x. But what about sine of x? Because we also want to get sine of x now. And that's the last one. So let's do sine of x as well. So remember, we're going to use the exact same method that we just used for cosine of x. We're going to just find the double angle of that half angle. Okay. So we can rewrite it as sine 2 of x over 2, right? Because eventually these 2's will cancel. But that's not what we're going to do yet. Because we're actually rewriting sine of x as the double angle of sine of x over 2, where they will cancel. But in this case, we want to keep x over 2 as the angle. Okay, great. From here, we need to recall the double angle of sine, but in terms of x over 2 being the angle, which is going to be 2 multiplied by sine of x over 2 multiplied by cosine of x over 2, which is still equal to sine of x. Okay, great. And we know what sine of x over 2 is and cosine of x over 2, right? We kind of did it here already. So sine of x over 2 is actually equal to t over root 1 plus t squared. So we can write it like this. It's going to be 2 multiplied by t over root 1 plus t squared, multiplied by the cosine of that half angle, which is 1 over root 1 plus t squared, right? Recalling from what we've done. And that's equal to sine of x. And then here we can just simplify. 2 multiplied by t, so 2 multiplied by t multiplied by 1, that's just going to be 2t. Divided by, and then we're going to multiply the denominators together. And we're multiplying two square roots, meaning that we're just going to be left with the expression inside of the square root, which is going to be 1 plus t squared, which is equal to sine x. Okay, so now we found our sine x, and we also found our cosine x. So now we can just do the substitution. So let me just skip to the part where I actually substitute. Alrighty, so we are back here. Obviously this 2 is here because I took it out from what we had here. I took this 2 out as a constant, okay, and we can do that. So let's continue, right? Here is what we have so far with all the substitutions, okay? So let's just actually simplify the denominator so we can write it as one expression. So this is going to be equal to 2 multiplied by the integral of everything in the denominator. I'm just going to do this over here. 4 multiplied by, so we're going to multiply the 4 by this whole expression in the numerator, which gives us 4 minus 4t squared divided by, and it's going to be 1 plus t squared, right? Minus, and we're going to actually multiply this 3 into the numerator, which is going to give us 3 times 2, which is equal to 6. So it's 6 multiplied by t. Divided by 1 plus t squared. And then all 1 is in the numerator. Multiplied by 1 divided by 1 plus t squared dt. Okay. Here we can see we have the same denominators. So we can write that as one expression. Okay. So now we're going to be left with equals to 2 multiplied by the integral of 1 divided by, and then we're going to have 4 minus 4t squared minus 6t divided by, so let me actually write it like this, divided by 1 plus t squared multiplied by 1 over 1 plus t squared dt. And then here, what can we actually do from here? Well, we actually have 1 divided by 1 in the numerator, all divided by, so the main divider over here, by some other fraction. And we can actually tip in times such that we can have the following over here. And I'm going to skip this step so that we are left with 1 plus t squared divided by 4 minus 4t minus 6t multiplied by 1 over 1 plus t squared dt. Obviously in this step I kind of skipped it because I tip in times, okay, so that I get all of this. And then what do we notice? Well, the 1 plus t squares can cancel, and then we are left with the following. We are left with this being equal to 2 multiplied by the integral of 1 divided by 4 minus 4t minus 6t dt. Looks very, oh whoa, and then I think there was a square somewhere here. Whoa, that sneaky little square, that looked a bit weird for a moment. So that's what we have so far. Okay. So let's kind of simplify this a bit. We factorize 2 out, take out 2 as a common factor, so that we are left with 2 multiplied by the integral of 1 over, and then we're going to have 2 in 2. That's going to be 2 minus 2t squared minus 3t, like that, dt. And then obviously this 2 can cancel with this 2 outside. And then we are left with the following. I'm actually going to write it like this. I'm going to take a negative out as a common factor and take it out of the integral such that we are left with 1 divided by, and then it's going to be 2t squared plus 3t minus 2. Okay, I kind of had to like observe that in more detail. Okay. And if you were to use the grouping method or the quadratic formula, you would get the following. So it'll be equal to negative. We're factorizing the bottom here. This can be factorized into 2t, and it'll be plus 1, and then t minus 2. Or wait, whoops, sorry, wrong way around. Minus is here, plus is here. Okay, so it's 2t minus 1 multiplied by t plus 2. And it's going to be dt. Okay, cool. And then from here, what are we going to do? Well, we are going to do partial fraction integration, our favorite part of integration. Oh my goodness. Okay, so let's do that. Okay, so what we have is the following. So we are going to take the integrand out, and we are actually going to suppose that 1 divided by 2t minus 1 times t plus 2 is equal to, and then what we are going to have is it's going to be a over 2t minus 1 plus b over t plus 2. And if you're unsure, you can check out my partial fraction integration video. It'll be on the card above on the top right of the screen. It should be. There it is. Yeah, I can see it. I can literally see it right now. I'm kidding, I can't see it. Okay, such that then we have the following, right? So we have this being equal to, we're going to take the lowest common denominators so that we are left with a multiplied by t plus 2 plus b multiplied by 2t minus 1 divided by, it's all divided by 2t minus 1, and it's going to be t plus 2, and then we have 1 divided by 2t minus 1 and t plus 2, like that. Okay, and then the denominators can cancel each other because they are like denominators. 1 equals to, we are going to multiply the a in already, so it's a multiplied by t, which is at plus 2a. Okay, so this looks like a t, there we go, plus 2a plus, and then we're going to multiply the b into these brackets here. It's going to be plus 2b times t minus b. Okay. From here, well, we can actually just group them together. So whichever ones has t, we are going to group them together. So in our case here, it's a and it's also 2b, positive 2b. So we have a plus 2b, common factor of t. And then we have plus 2a minus b, which is all the constant, which is equal, which is going to be equal to 1. Everything equal to 1 in this case here. Okay, cool. And then, well, we have t on this side, but we don't have t on that side. So we can actually rewrite it as 0 times t plus 1, because this is a positive 1 anyway. 0 times t implies to us that we can actually do the following. We know now that because this can satisfy the equation, we need to suppose that 0 is equal to this coefficient here of t. So the coefficients of t and the constants respectively need to be equal to each other. Okay, so 0 is going to be equal to a plus 2b, and 1 is equal to 2a minus b, and then we just need to solve from here. So here we're going to have a is equal to negative 2b, so let's do the substitution from there. We're doing a substitution. That's going to be 1 equals to 2 negative 2b minus b, like that, right? Then we're going to simplify. 1 is equal to 2 times negative 2, which is equal to negative 4b, minus b, which is equal to negative 5b, and therefore b is equal to negative 1 over 5. And now we can plug that back in. A is equal to negative 2 multiplied by negative 1 over 5, where a is therefore going to be equal to negative, and a negative gives a positive, then it's going to be 2 over 5. Okay, so now that we know what our a and b are, we can plug it into our integral. Here we're going to have the integral of, was there any constant? I just need to remember. Okay, now, oh, there was a negative. So we're going to keep that negative here, remember. It's negative integral of, we're going to be using the a divided by 2t minus 1 plus b over t plus 2, which was our integrand that we had. Remember, we supposed that 1 over that is equal to all of this. So we're just doing the replacement, such that we know what our values of a and b are. So let's just do that. So we're going to take the integral into both the terms and also plug in the constants and take the constants out. So we have negative a, which is 2 over 5, integral of 1 over 2t minus 1. Okay, dt. Minus, the negative goes into the positive, gives minus, then it's going to be negative 1 over 5, so let's make that a positive now, because the negative is going to cancel the negative out to give a positive, and then it's going to be 1 over 5, integral of 1 over, and then we're left with t plus 2 dt. Okay, from here, what are we going to do? Well, we are going to integrate now. We can actually integrate, right? So we can write this as negative 2 over 5, and we have 1 divided by some function, linear function, meaning that we can now do, and it's a function to the first degree, so we are allowed to do the natural log integration. So here it's going to be negative 2 over 5 times the natural log of absolute value t, 2t minus 1, and it's going to be plus 1 over 5 multiplied by the natural log of absolute value t plus 2 plus c. But now remember that we need to end our answer in terms of x. So we know that t is equal to tangent of x over 2. So let's go back. Wherever we see t, we're replacing with tangent of x over 2. So negative 2 over 5, natural log of absolute value 2, tangent x over 2, minus 1, plus 1 over 5, natural log of absolute value tangent of x over 2, plus 2, plus c. And that is our final answer for our first integral. That was a lot of work. And I'm going to be honest with you, I have not done the solution. But hey, that was a pretty good solution, I can't lie. So that is that integral. Now what we're going to do, we're going to go to the second one. I think it'll be a little bit more easier. We'll see. But yeah, let's move on to the next question. Oh my goodness, here we go. We're finally on the next question. I didn't even expect the first question to be such a long solution. But anyway, let's do this, right? Now we have the square. And if you can remember from the beginning, we said that when we have a square in the trig function, we are going to suppose that t is going to be equal to tangent of just x. Now we're making life much easier for ourselves. Now we need to use reference of our triangle again. Nothing's going to change in our triangle. So we're going to have x being the angle. We're going to have t and 1 over here. And then once again, the hypotenuse is 1 plus t squared. Root 1 plus t squared, sorry. From here, we're going to differentiate both sides. We're going to have dt equals 2. And then we're going to have secant square x, dx, right? Such that we will have dt is equal to, remember, we're using identity because we have it in terms of, apologies about that, oh yeah, we're using the identity secant square x, which we can rewrite as 1 plus tangent square x dx, okay? And then from here, we know that tan x is equal to t, so we can actually rewrite this as 1 plus t square dx equals to dt. And then from here, we know that dx is going to be equal to dt divided by 1 plus t squared, if we take the 1 plus t squared over. Okay. From here, what are we going to do? Well, we have dx, and now we can replace dx in terms of t. Okay, so let me just do that quickly. Alrighty, cool stuff. We made it here already. So what are we going to do from here? So I did the substitution here, and I just wrote down the dt over here, okay? And then what we're going to do now is we need to now replace cosine square x, or just cosine x, and this one over here, we need to replace the sine x, and we need to have it in terms of t. So we need to use reference to our triangle. So let's do cosine. We will have the adjacent of the angle divided by the hypotenuse of the angle, x, which is our cosine. Remember, we're trying to find cosine of x. Okay, so here we're going to have cosine of x. Perfectly, it's just going to be equal to 1 over root 1 plus t squared. We don't have to do any manipulation here because we already have the angle x. Okay, over there, and note over here that what we have is it's actually squared. So I'm actually going to add the square in, right? I'm going to add the square in for now. So we're going to rewrite it as cosine square x is equal to that. Okay, we squared both sides, such that cosine square x is actually just going to be equal to 1 divided by 1 plus t squared, using the exponential laws of fractions. Now we found our cosine square x. Just like that, we found it. Now we need to find our sine square x. And remember, it's just sine x but squared, which was represented as the opposite over the hypotenuse of the angle x. So it's t over root 1 plus t squared. So it's t over 1 plus, root 1 plus t squared. And remember, we squared both sides, such that we'll have sine square x is equal to t squared divided by 1 plus t squared. Found sine square x. That already, we've literally just done it. From here, what are we going to do? Now we're going to do the substitution again. We're going to substitute back what we actually just had. So this is going to be written as follows. Let me just skip to that part again. And voila, this is what we have. So now we just need to simplify the denominator, right? We did all the substitutions. Now we're going to rewrite it, right? But now notice that this term is the only one that doesn't have a denominator of 1 plus t squared. So we're going to rewrite it as 5 into 1 plus t squared divided by 1 plus t squared. And this is going to be plus 4. We're going to multiply the 4 into the 1, so it's going to be 4 over 1 plus t squared minus, and we're going to multiply the 4 into the t squared, so it's 4t squared divided by 1 plus t squared. And then we have this in the denominator. So funny over here, right? Multiplied by 1 over 1 plus t squared dt. Whoa, and now we can write down everything in one fraction. So let's do that as well. So this is how it's going to look. It's going to be equal to the integral. Write down the line already. We're going to multiply the 5 into the bracket so that we have 5 plus 5 t squared divided, not yet, plus 4 minus 4t squared. Okay. Divided by 1 plus t squared. And then this line will be shorter. All divided by 1. Or the 1 is in the numerator. Multiplied by 1 over 1 plus t squared dt. Which now we can rewrite it as follows. Because this is 1 divided by 1. Divided by this whole denominator. We tip in times and we get something like 1 plus t squared divided by, and then everything in that numerator of the denominator, which is 5 plus, we can actually simplify this over here, 5t squared minus 4t squared, which is equal to t squared. And then this is going to be plus 4. So actually, we could have done 5 plus 4, which is equal to 9. So this is actually going to be plus 9. Multiplied by 1 over 1 plus t squared dt. And note, these can cancel. And then what are we left with? We are left with the following. This is going to be equal to the integral of 1 over, and we're going to have t squared plus 9. But we can actually rewrite this 9 as 3 squared dt. Now, if you remember with using reference to our trig substitution, some students, they didn't learn trig substitution yet. In our case, our class accordingly, but should I use it? Let's actually just use our property that tells us, let me do it in blue, our property tells us that if we have the integral of 1 over x squared plus a squared with respect to x, this is equal to 1 over a multiplied by arctangent of x over a plus c. So that just tells us that our a value is being squared. And the reason why I wrote 9 as 3 squared is because this 3 over here is represented as our a value. And t is actually our variable, which is actually kind of x. So let's do that substitution. Equal to integral And what we are saying here, we don't actually have to do the integral, we can just do the substitution here. Our a value is 3, so here 1 over a, which is 1 over 3, arctangent of x over a, in this case it's x over 3, plus c. But it's not x, I just remembered, sorry, it's t. Because our variable is t. And then remember, we let t be equal to tangent of x. So therefore, we are actually left with a final answer of 1 over 3 arctangent of tan x divided by 3 plus c. And that is our final answer. So you can see that the one with the squares is a lot more simple and easier to integrate compared to the one without the squares.